What we're going to talk about today is the new chapter on divisibility. So we've been hinting at things like this number divides this number and so on, but we didn't really talk about the ins and outs of how that works. And chapter 6 is the first time that we're actually really digging deep into what it means for a number to divide another number. And if you're worried about all this stuff, don't worry, that was just fun stuff we were doing before class. So I'm going to delete all that. Just an announcement, I've got to cancel my office hours this week. Sorry, folks. You can always put on Piazza, you can always message me on Discord, you can always email me. So I'm sorry that I'm canceling my office hours, but I just had some extra stuff to do. So what divisibility is good for? We'll see today a couple things. There's some theorem about remainders, that was from the textbook, but then we're going to use remainders to prove some things that we were working with in the past. We had to remember we had problems like prove that this equation has no solutions. So here's an example. Prove that, let's say y squared equals 5x minus 2 has no integer solutions. In the past, how would we do that? How would you try to attempt to prove something like this? Yeah, by contradiction. So we're still going to do that. We're still going to do contradiction, but now it's going to, the argument's going to involve something with division, and it's actually going to be kind of cool. So let's get started with that. To start us off, ignore this stuff. That was just fun stuff. Here's a question for you that's kind of similar, but a simpler one. Does this equation, 13m plus 7 equals 13n plus 9, does this equation have any integer solutions? Let me pop up that poll for us. Yes or no? And of course, you have to justify your answer. Okay. Can someone, would someone want to explain their answer? Why they would choose B or A? Anybody want to share?
So what I did is that, you have 13m plus 7 is equal to 13n plus 9.
Yeah.
So I moved all my terms with m and n onto the left side and all my numbers onto my right side. So you get 13m minus 13n is equal to 2. So yeah, so then I just factored out the 13. So then m minus n is equal to 2 over 13.
Yep.
And from there, this was more just of a, I didn't really know how to say this in proper terms, but I was just reasoning that you cannot subtract two integers and get a fraction.
Perfect. That's a really great answer. Thank you, Mahadis. It's a great answer. See, m minus n, when you subtract two integer, again, you got an integer, right? So, but m minus n is an integer, while 2 over 13 is not an integer. So there's a contradiction, hashtag contradiction. Right? Here's a way, okay, so the thing is, imagine you're on an alien planet where nobody knows what a fraction is. So nobody's ever seen 2 over 13. If you divide by 13, imagine you're on an alien planet where that's the same as division by 0. They're just like, you can't divide 2 by 13. That's not an integer. So what would you say at this point? Because you're not allowed to divide by 13. What's an alternate way to say the exact same thing Mahadis just said? From this point up here. Two does not divide 13. Other way around, right? This is saying that 13 divides 2, right? An alternate way to say this, you could say from 13 m minus n equals 2, you can say 13 does not divide 2. Right? That's another way you could say it. But then there's actually one more way to do it that uses remainders. What you can do is say, well, look at this division, right? This division is saying, okay, see this integer here, right? 13m plus 7. What's the remainder when you divide by 13? 7. But on this side, 13n plus 9, the remainder is 9, right? So another alternate way to say it is 13m plus 7 has remainder 7 when divided by 13, right? But 13n plus 7 or plus 9 has remainder 9 when divided by 13. What's the contradiction here? If these two numbers were equal, what's a contradiction? Different remainders, right? If you divide a number by 13, there's a unique remainder. Contradicts unique remainders. Okay. See what's going on? When you divide a number by any other number, the remainder is always unique. So here, let me see what's next. Okay, actually, let me just state that theorem. What's that theorem called? Exactly, Tim. That's right, the division algorithm. The division algorithm states that if you take a number A and divide it by a number B, there's always going to be a quotient and a remainder. The thing is, the quotient and the remainder are always uniquely determined. There's only one quotient and one remainder. So the theorem is like this. For any integers A and B, let's say for any natural numbers A and B, if, let's say like this, there exist unique integers Q and R such that A equals B times Q plus R. And Q here is the quotient, while R here is the remainder. So the fact that remainders are unique means that you can't take a number and divide it by, for example, 10 and get a remainder of 5, but then you divide it another way and you get a remainder of 7. That doesn't make any sense, right? The remainder is always, you're only going to get one number out as the remainder. Anybody remember how to prove this theorem? This is actually an innocuous enough statement. We've known about remainders since elementary school. But how do you actually prove that the remainder exists? What's the style of the proof for that? From the textbook, from the textbook. Very good, nice. Meg and Nishav read the textbook. So this is induction. Remember, you use strong induction for this one. And here's my next question for you. Open up the textbook, have a look at that proof. If it's a strong induction proof, that means the induction hypothesis has to be used somewhere, right? Where exactly was that induction hypothesis used? Okay, where exactly was that hypothesis used? Open up the book, have a look. So here's the division algorithm, right? A equals QB plus R, and let's just scan the proof and see why it's by induction. So they state here strong induction, and then they do a bunch of cases. So K plus 1 is less than B, K plus 1 equals B, and here we go. In this case, we use the induction hypothesis. So it's in the case where K plus 1 is greater than B, right? Let's go back there. Okay, and so it looks like it's this third case here. K plus 1 is greater than B. So there's the answer. What was I missing from here? What was I missing? Nice. Yes, I'm missing, I guess, two things. I should have said that Q is non-negative, where Q is non-negative, and R is between 0 and B, not inclusive of B. Okay. Okay, any questions about this one? I clear up about the division algorithm? Okie dokie. Let's use the division algorithm for a nice numerical, a very simple numerical problem where you get to apply the theorem in some kind of neat way. So here's a number 10 to the power 20 plus 5 to the power 8 plus 3 to the power 4. When you divide that by 5, what's the remainder? And if you try to do this by actually calculating 10 to the power 20, you're going to have a bad time. So you got to be a little bit thinking about the division algorithm.
Okay, so my answer was 1. And the reason I got 1 is because I know that 10 to the power of 20 is divisible by 5. So I know its remainder is 0. I know 5 to the 8 is divisible by 5. So I know its remainder is 0. So I kind of ignored them. So now I know that just the remainder of 3 to the 4 divided by 5 is going to be my whole remainder. So 3 to the 4 is 81. And the remainder of 81 divided by 5 is 1. So I know that
Nice.
my remainder would be 1.
Nice. That's good reasoning. That's good reasoning. So he's just saying that these 10 to the 20 and 5 to the 8 don't contribute anything to the remainder when you divide by 5, right? One way to see that with the division algorithm is, let's apply that theorem, right? A equals BQ plus R. So what should A be and what should B be? BB. A should be this number, 10 to the power 20 plus 5 to the power 8 plus 3 to the power 4. What should B be? Yeah, I'm dividing by 5. So let's divide out by 5. Now I want to write A equals B times 5, or sorry, 5 times Q plus remainder, right? So what I can do, how can I do that? What's the Q and what's the R? And remember, I need R to be between 0 and 5, right? So R is 0, 1, 2, 3, or 4.
Could you not set Q in terms of R and then substitute it back in?
I see what you're saying. How do you suggest to do that exactly?
Because A is going to be that whole 10 to the 20 plus 5 to the 8. And then you could just take the R to the other side, then divide by 5.
I see. Okay. Okay, but you don't know what R is yet, right?
No, you're not. You're trying to find it.
Yeah.
So you
Here,
could you could back sub in Q, and then you would just have an equation in terms of R.
I see what you're saying. So you want to find R. Okay, so you want to, but okay, hold on. Maybe I don't understand what you're saying. I think my approach would be like factor a 5 out of the A, right? So where can I factor a 5 out?
But you can't take it out from the 3 to the 4.
I can't take it out from the 3, no. So what I can do is factor a 5 out from these first two terms.
Okay.
See what I'm saying?
And
the answer is A. That is correct, what Mahad has said. Here, this is what I was thinking. I was thinking take take this 10 to the 20 plus 5 to the power 8 plus 3 to the power 4 and factor out as many 5s as I can. So I can write this as 10 to the power 20, or maybe I'll write that as 2 to the power 20 times 5 to the power 20 plus 5 to the power 8 plus 80 plus 1, right? Because I want to factor out as many 5s as I can. So I split the 3 to the 4 into an 80 plus 1. Because I want to pull out I'm dividing 81 by 5, basically, right? And when I do that, how can I factor out a 5? 5 times what? It's, how do I factor out a 5 from here? What's left over? I get 2 to the power 20 and then 5 to the power 19, right? And then I have 5 to the power 7 plus what's 80 divided by 5? 16 plus 1. So here's my Q and here's my R. 5 times something. Division algorithm says 5 times something plus remainder. So R equals 1. See my logic? What Mohada said is right as well. You could just divide out each term and then look at the remainder, look at the remainders of all the terms and add those up, basically. You could just more or less do that. And by the way, this is a Q, not a 9. Q.
咱们什么时候给我做好哪些丸子呀？
Uh-oh.
又没红豆做
Oh, make sure you're
照
muted.
片就出。
There we go. Okay, so I got one more polling question for you guys, unless there's any questions about this one. I think what Burgess was saying ultimately makes sense, right? You could subtract 1 from both sides, or subtract R from both sides, perform this division, and then add the R back in, and you'd get R equals 1. That would work too. Should it be 2 to the 10 times 5 to the 10? I don't think so. If you have x times y to the power 20, that's x to the 20 times y to the 20, right? You just distribute the exponent out. I don't know how you guys are getting to the power 10. What happened to the power? You shouldn't decrease the power to 10, right? Make sense? Did I make a mistake? Let's go to the next polling question here. One more, similar flavor. So now take any odd number and square it. How can you find the remainder? How can you find the remainder? Looks like overwhelmingly B is the answer, or B is voted.
Hi, Professor.
Yeah.
So my way to do that is like I write odd number into the form of 2n plus 1. N is for all real, not real number. It's this is called the natural number. Yeah.
Yeah.
So I wrote 2n plus 1 square equals 4n squared plus 4n plus 1. And then we can just pull 4 over, and then we can have 4 times square n sorry, 4 times n squared plus n plus 1. So we can get the remainder is 1.
Very good. Perfect answer. I don't even need to take this one up. This is correct. So when you square an odd number, what you do is you expand this out and try to see, can you write it as BQ plus R, where B is 4, right? In this case, B is 4. So here's Q and here's R. And since R is between 0 and 4, or well, 1, 2, or 0, 1, 2, or 3, you can see that this is the remainder right here. Nice, good answer. Anything I can clear up about what he just said? Basically, if you can write this up.
Sorry, I had one question. Is that just with this method where x is equal to 2n plus 1 to signify an odd number, because if n is natural, would that kind of excludes the possibility of x being 1? I'm just, like everything else works, I understand, but
Okay,
how would we
okay,
be able to?
Well, what would n be if x was 1?
It would have to be 0.
Sure. So why don't we say n is a natural number or it's 0?
Okay.
Now we're good, right?
Oh yeah. Okay.
You can always make restrictions like that. In fact, non-negative integers are often just as useful as positive ones. 0 is sometimes useful to include. Yeah. Good question.
Okay.
Actually, I think we can also write it as x equals 2n minus 1, and we will get the same answer.
Yeah, good. That works too. You could also do that. Perfect. Awesome. Okay. Is there anything extra that I can clarify about this stuff before we move on to the exercise? How did we deduce Q? Basically, I want to divide by 4, right? And if I want to divide by 4, then I need this thing to be in the form, what I needed to get was x squared equals 4 times Q plus R. right? Where Q is non-negative and R is between 0 and whatever 4 or whatever I'm dividing by, in this case 4. So where R is 0, R is between 0 and 4 inclusive, or sorry, inclusive of 0, exclusive of 4. You see? And so what I'd want to do is factor out as many 4s as I can. So I did that. And if there were any more 4s left, I would have factored those out too. I factor as many 4s as I possibly can. Whatever's left is the remainder. Just like in grade 4, right? Just like in elementary school. How do you get the remainder? You factor out as many of the denominator as you can, and whatever's left over, that's the remainder. Actually, let's use that technique again in the following exercise. If you guys are ready to move on. Watch this. Here's another exercise. This is the one I said at the beginning of class. Here's an equation with integer variables. So y squared equals 5x minus 2. This is a tricky exercise. Prove that this equation has no integer solutions. Think about the way we've done it in the past, but now apply the division algorithm. And since there's a 5 here, I have a little hint for you. Try dividing by 5. What could possibly happen, okay? How about I give you guys 10 minutes to work on this? Plus another couple minutes if you need it, and then I'll take it up at the end. Does anyone want to turn on the mic and maybe share their idea for how to solve this problem? If you got anybody who was able to solve it, and if you didn't solve it, that's okay. If you want to maybe start me off on what your idea was. Anyone who wants to come on the mic there.
Professor, I would like to go.
Yeah, sure. Let's hear it.
So what I did was I divided the whole equation by 5. That's y squared by 5 equal to x minus 2 by 5.
Okay.
And then I took minus 2 by 5 to the left-hand side. So basically I isolated x. And from this, we can suggest if x comma y belongs to an integer, then x will always be an integer. So x cannot be an integer solution.
I see. What if this was 3 over 5 though? What if y squared over 5 was 3 over 5? Then you would have 3 over 5 plus 2 over 5, which is 1, and that would be an integer, right? Right? You see what I'm saying?
Yeah. But
what if y squared over 5 was enough so that it would become, oh, no integer equals 3? Okay, sure. But it doesn't have to be 3, right? What if y squared was 8, right? Then you could have y squared equals, or you could have 8 plus 2 would be 10. 10 over 5 is 2. X would be 2. That's not a contradiction, right? You'd have to show that y squared can never be a number that will make an integer here, right? So you'd have to show, yep. So what you'd have to show for this is you'd end up with a y squared. Well, here, sorry, maybe I should have written like this. You would end up like this. And I think I'm going to run out of time. So ultimately, you would have to show that y squared is not divisible by 5. Right?
Makes sense. Yeah.
Right. And that's equivalent to this problem anyways. So I like your approach. How do we show that y squared is not divisible by 5? That sounds like a good idea, right? So let's write it out. I think that's actually a good idea. That's going to go somewhere. So let's try like this, right? Divide by y, apply the division algorithm to y, to y. So divide by 5. What does that mean? That means y equals 5 times q plus what? Plus r, right? Right. I should say, suppose for contradiction that the equation does have a solution, right? I should have said that. Suppose there exists integers y and z, x and y, such that y squared equals 5x minus 2 for contradiction. I should have said that, but okay. So now I have y equals 5q plus r, where I know that q is non-negative and r is between what? 0 and? 0 and q. Yeah, exactly. And q is, no, not 0 and q. Not quite. 0 and 5, right? And if r is between 0 and 5 and not inclusive of 5, the only possibilities are 0, 1, 2, 3, and 4. So I've got 5 cases for what r is. So let's square both sides. So now if y squared equals 5x minus 2, what can I do? I can say that 5q plus r squared equals 5x minus 2. Let's expand. 25q squared plus 10qr plus r squared equals 5x minus 2. Anyone get this far? Anybody know what to do next? Have an idea? I'm dividing by 5, so what should I try to factor? Factor out as many 5s as I possibly can. So if I factor out 5s here, from the 25q squared, from the 10qr, and the 5x, this becomes like how exactly, right? R squared plus 2 equals 5 times 5q squared plus 5q, nope, plus 2qr plus or minus x. Sorry, what have I done? X minus 5q squared minus 2qr. There we go. So what does that tell me? R squared plus 2 is a multiple of 5. See what's happening? What can I do? How can I finish off the problem? Why is there a contradiction that r squared plus 2 is a multiple of 5? And notice that this is very similar to what Muhammad was saying earlier, right? Muhammad was ultimately, his argument ends up saying, can y squared plus 2 be a multiple of 5? We have to argue by contradiction. What's nice here is that now I have r squared plus 2, and I know there's only 5 possible values for r, right? So let's do cases. What Burgess said, cases. If r equals 0, I get 5 divides 2, which is a contradiction. See? If r equals 1, then I get 5 divides what? Sorry, maybe I should have expanded more here. I should say 5 divides r squared plus 2, which is 2, right? If r equals 1, then what's r squared plus 2? That's going to be 3, but 5 does not divide 3. So I've got a contradiction here too. If I do r equals 2, I have 2 squared plus 2, which is 6. But 5 does not divide 6, and I've got a contradiction. You see what I'm doing? Every case I'm getting a contradiction. R equals 3 implies r squared plus 2 is 11, right? 9 squared plus 2 is 11, but 5 does not divide 11. Contradiction here. And the last case, if r equals 4, then I have 4 squared plus 2, which is 18, but 5 does not divide 18. I've got a contradiction here. Contradiction in every case. That's the whole proof. Okay, I see a lot of questions in the chat. Let me take them.